Hello, my name is Gustavo Espinosa, and I'll be walking through the first Physics 2 lab, the Charged Tape Lab. Here are some of the key concepts that this lab is aiming to go over. The first one is the concept of charge as a property of matter. The second one is the effect of this property in the real world. And the last one is using a computational model to model the real-world systems. In this case, we will be attempting to model the interaction between two charged pieces of tape. In this lab, we will be using a charged piece of clear Scotch tape and approximate the amount of excess charge on that piece of tape. Here are some of the key concepts we will be using for this experiment. The first is the idea that two like charges are going to repel with equal and opposite magnitude to each other, and two like charges are going to attract. The second concept uses Coulomb's law in order to determine the electric force caused by the excess of charge of one particle onto another particle. The 1 over 4 pi epsilon naught is actually a fundamental constant, which we're going to represent as k, which is roughly equal to 9 times 9 to the 10th power newtons meters squared over coulombs squared. We're going to be using some everyday household objects for this experiment, some of which include a roll of clear Scotch tape, a ruler, a flat surface to work on, and two thick books or any stackable objects. The first step in the procedure for this experiment is to create our charged piece of tape, called the U-tape. On a flat surface, place a piece of tape about 20 centimeters long and use your hand to smooth it out. This creates the base tape as seen in the diagram. We then grab another piece of tape about the same length and fold one end of the tape to create a handle that we can use to grab onto it without touching the sticky side. This creates our U-tape. We then place the U-tape on top of the base tape, and while grabbing onto the handle that we made, we pull the tape off quickly, and we are left with the charged U-tape. The next step in the procedure is determining the charge of the tape. First, in order to identify if the tape has been charged correctly, place the tape on the edge of the flat surface so that it may hang off, as shown in the figure above. Then, as you slowly move your hand closer, you should notice that the tape moves on its own and sticks to your hand. This is because we have a charged tape that is attracted to your hand. Then, we observe its relationship with differently charged objects to determine the sign of the charge. For example, when we hold another piece of charged U-tape close to the tape that is hanging off, we can observe that the two pieces repel each other. We can conclude that the two tapes must have the same sign of charge. Then, in order to determine the actual sign of that tape, we can negatively charge a pen by rubbing it on cloth and observe that the pen attracts the tape. Because of this final interaction, we can conclude that the pieces of charged U-tape must have an equal positive charge. Some important assumptions for the experiment are as follows. We must treat the tapes as point charges. The tapes hold the same magnitude of charge, and the tape's mass is proportional to its length, in this case 1 gram per meter. And finally, that air resistance is negligible. Now for the experiment. We place one U-tape on top of a stack of books so that there is slack and there is space underneath. Then we record the length of the B tape in order to later determine the mass. Then we grab another U-tape and hold it in our hands. This becomes our A tape as seen in the figure. Then we move the A tape towards the B tape until the B tape begins to float. Once the system is at equilibrium, we record the distance d, the distance between the two floating tapes. Some of the recorded values include the tape length of 24 centimeters for both pieces, tape width of 2 centimeters for both pieces, the distance d between both tapes being 3.5 centimeters, and some of the calculated values are the mass of the tape, which we determined using the mass to length ratio of 1 gram to 1 meter, equaling 2.4 e to the negative 4 kg, and the number of atoms, which we determined by taking the surface area and dividing it by the area of an atom. The first calculation that we did was determining the force of gravity on tape B. Then, because the system is at equilibrium, we set it equal to the electric force equation that we found earlier to determine the charge to be 1.8 times 10 to the negative 8. Then, we divided that by the charge of a single electron in order to determine the total number of excess electrons in the system. For the ratio of electrons to atoms, we simply put the number of electrons over the number of atoms that we found earlier and got 2.33 times 10 to the negative 7. In order to better visualize this, we used a computational model. Some of the code to make the model is being shown, with specifically the code to set up the charges and represent them as spheres. The other code is used to determine the electric field and force on our point charges. This is the output of our model, with the floating tape being represented by the red sphere and the secondary tape being modeled by the blue sphere. The forces acting on the 2 points are represented by different color arrows on the screen. The output at the bottom shows the estimated gravitational force, electric field, and electric force. Finally, because we are assuming that the gravitational force is equal to the electric force, we have the difference of the two to show the margin of error in the calculations. Finally, we have some additional questions, such as what if electrons had positive charge and protons had negative charge? What would change about the observations that you made with your tapes and other charged objects? The observations would remain the same during the experiment because the tapes would still repel each other with the exact same magnitude. Objects that are similarly charged would continue to repel each other, and objects that are oppositely charged would continue to attract. Why is it important to handle the charged tapes with as little as possible? What happens when the charged tapes come into contact with your hands or other objects? Well, when charged objects come in contact with other objects, the excess electrons that the tapes would hold are transferred to the other objects, and therefore lose their overall charge with every touch.